Now we're being asked to find the scalar and vector projections for these two vectors, vector B onto vector A. Let's start with the vector projection. And as we've seen, the vector projection formula is going to be the projection of B onto A is given by the dot product of A and B divided by the magnitude of vector A quantity squared. All of that is one giant scalar that is then going to be multiplied by or extending or shrinking the vector A. So it's a scalar multiple of our vector A. In order to determine this projection vector, the first thing that we'll need to do is determine the dot product and then the magnitude of A. So the dot product of A dot B is going to be 3 times -1, so the x components multiplied together, plus 3 times -1 again, which are the y components multiplied together, plus 4 times 2, which are the z components multiplied together. And then we just add all this stuff up. So this is going to be -3 minus 3 plus 8, which is +2. So that's the dot product of A and B. Then we need to find the magnitude of A, and we'll say the magnitude of A is going to be given by the square root of -1 quantity squared. We're squaring the components and adding them together to get the magnitude, and then find out what this number is. So we're going to have 1 plus 1 plus 4, which is the square root of 6. So now we'll take this 2 and the square root of 6 and pop it up into that projection vector formula. So we have the projection of B onto A is given by A dot B, well that was 2, so we'll put the 2 there, divided by mag A squared. So mag A is rad 6, and we're going to square that quantity. So then that's going to be our scalar multiple of our vector A. So let's simplify that. So that's going to be 2 over 6, or let's actually go ahead and just change that to 1/3. So 1/3 is the scalar multiple of vector A. Vector A was -1, -1, and 2. So to get our projection vector, we're simply going to distribute that 1/3 into that vector A. So this will be -1/3 minus 1/3 and then 2/3. So this is what we call our vector projection of B onto A. Now, to get the component of B onto A, which again is the signed magnitude of the projection vector, meaning that it can be plus or minus, and it's going to basically give us the magnitude of that vector. If the component of B onto A is plus, that means the angle in between the two vectors is somewhere in between 0 and 90 degrees, essentially that they're going in the same direction. Or the same general direction. If the component of B onto A is minus, that means that the angle in between the two vectors is going to be greater than 90 degrees, but of course always less than 180 when we're the angle in between two vectors. So the formula for determining the component of B onto A is A dot B over mag A. We've already found these two quantities, A dot B up here being just 2, and mag A is rad 6, so we've got 2 over rad 6, and so this will be our magnitude of the projection vector. Let's see how big that is. So if we just throw that into the calculator, we get the decimal quantity 0.816, so kind of a small magnitude there, but just noticing that it's positive. That means that my projection vector is going to be going in the same direction as the vector that we are projecting onto, which means in the same direction as A. So let's now take that over to GeoGebra, geogebra.org, and we're in the 3D graphing calculator. We type in a lowercase letter and then open up parentheses, and let me actually show that down here. So I'm going to choose just a different letter. So lowercase letter equals open parens 3, 3, 4, and then when I close the parens and hit enter, it automatically turns that into a vector. So that's the syntax for getting a vector into GeoGebra. I'm going to delete that one because I've already got it up here, and say I'm going to turn it on here, and we see that this is our B vector. I'm going to slide this around so we're looking kind of at the first octant with a positive x axis in this direction, positive y, and positive z. So our B vector is coming out at us in the first quadrant. If we lay A in as well, we're going to have to twist around a little bit to see how these two are related to each other. So I'm going to twist my plane or my coordinate system around so I can more easily see that for sure the angle in between the two vectors does seem to be less than 90 degrees, which is the reason, or verifying, that our component of B onto A should very well have been positive. Here is the vector that we got for our projection, and I just labeled it P for projection. If I turn that on, we can see that that vector is heading in the same direction as A, as it should, right? Because the projection vector is simply a scalar multiple of A, which means that it will be either heading in the exact same direction of A, or if the angle in between the two vectors is greater than 90 degrees, that projection vector would be headed back in this direction in the exact opposite direction of A. But either way, it is, I guess we can say, directionally similar to A, because the angle in between the two vectors is less than 90 degrees. That shadow, if we had a light up here casting a shadow down onto the tip of B, would be cast onto the A vector. So we can reinforce or just kind of get a general idea that our answer is probably correct, because that yellow vector does appear to be an appropriate shadow for this B vector down onto the A vector.